Alright, welcome back. This is going to be the last one for the week, and we are going to look at electrolytic cells. Of course, we are going to define what they are. Now, because it has the word kind of electro in it, that means in electrolytic cells, electrical energy is used to force a non-spontaneous reaction. So we looked at last week, or maybe it was the week before, either way, at some point in time, we looked at how to predict spontaneous reactions, and we can tell by the combinations if something's spontaneous or non-spontaneous. So the voltaic cells use spontaneous reactions to produce the electricity. Now these here, we can actually force non-spontaneous reactions. So if we want a reaction to occur, basically we just hook it up to a battery and fire some electrons into it, and boom, we can force her. So this is going to be the opposite of voltaic cells, of course. So kind of the comparison we have right here, if we have reactants, it's spontaneous and we produce our products and also going to produce electrical energy. So that's voltaic cells. If we start with some reactants and we have to supply electrical energy, that is going to be electrolytic cells and so on. So it is kind of the reverse. Now we still need electrodes, we still need an electrolyte, but the main source, or the main difference right here, we need a source of the electrons, so we need a power source. And this is one of the main differences. So if you are looking at a diagram of a cell and you notice it has a power source, right away you can tell that it is an electrolytic cell as opposed to a voltaic cell. Now, you will notice when we did a lot of our cell stuff here as well, when we did a lot of the reactions, and probably you did those in your own notes, we've seen positive values for the cell potential. That means it was spontaneous. Well, for our electrolytic cells, when you do your cell potential calculations, you get a negative value. And that is going to indicate that it is non-spontaneous, so it's not going to spontaneously produce electricity. But what that value tells us, if you do that calculation, that is the minimum amount of energy that must be supplied in order to get that reaction to occur. So it's not like you just toss in some electrons in it or electricity and then it'll go. That's kind of that barrier that we need to supply that amount of energy to get it to going. Now, some common uses for electrolytic cells, we have electroplating metals, so that just means deposit like gold, silver, bronze, or chromium on other non-useful metals like iron or nickel, or just metals that aren't really valuable, but we can plate a valuable metal on them. Of course, charging batteries, that is why we have to hook them up to the outlet in our houses and stuff like that, so it recharges batteries. And of course, another very useful one is splitting compounds. So this is how we can get hydrogen gas, oxygen gas, chlorine gas, and so on. So of course, electrolytic cells hooked up to a power source or a battery instead of an external circuit. So the electrons, the whole point of this battery, electrons are pushed from the anode and pulled to the cathode by the power source. So it's not physically pushing it, it's just something that is there, so it's using its own chemical energy to kind of force that reaction. Now, this little bit right here is going to be confusing, but we're just going to look at some of the common things or differences between voltaic cells and electrolytic cells. Now, the anode of an electrolytic cell is connected to the cathode of the battery. So because the cathode of a voltaic cell was the positive terminal, therefore, the anode of our electrolytic cell is going to be labeled as positive. And likewise, the cathode of our electrolytic cell is connected to the anode of our battery. Now, normally the anode of a voltaic cell is negative. So that means the cathode of our electrolytic cell is going to change polarities and also be negative. Another way to think about it is that if we're trying to reverse the flow, like just thinking about charging a battery, we're trying to kind of reverse the reaction, so we're reversing the polarities of our electrodes. That's another way to think about it, but we're not changing the direction of the electron, so that is something very important to remember. So the power source changes the polarities of the cell, which is fine. Now, for standard cells, all entities listed in the equation of a reaction are there. Now sometimes, standard cells contain all entities listed in the equation for a half reaction. They're measured at SATB conditions and 1 mole per liter. Now, non-standard cells don't have everything listed. they're not at SATP conditions. There's just a bunch of different things. So when we look at an example right here of a non-standard cell, we can still tell this is cell notation because we have our phase boundary right here. We can tell our solids are right here. We have 2 electrodes, and we just have 1 electrolyte solution, right? There's no physical boundary here. So, and we also notice that there's no lead ions and there's no zinc solid. So we're missing some key components. Now, when we look at what everything that's there, out of our entities, we got lead solid, we got zinc 2 plus sulfate, and of course lead solid. Now when we list out our entities, Pb solid, zinc 2 plus, SO4 2 minus, and of course our trusty water is there because of the aqueous. We can try to figure out what is our strongest oxidizing agent, strongest reducing agent by looking at our data booklet, right? And of course if you look at your data booklet and find lead solid and lead 2 plus, or sorry, just lead solid, lead 2 plus is not there, so forget I said that. And our zinc, you will notice they are, well, we have, I can't even find them. Our zinc 2 plus is all the way down here. We don't have zinc solid, so we cannot include that, but we have lead up here. Now notice this is a non-spontaneous reaction, right? So we can put that in. Lead is our strongest reducing agent, zinc is our strongest oxidizing agent, so we can fill these into our notes right here. So our strongest oxidizing agent was Pb solid, producing Pb2 plus 2 electrons. Our strongest oxidizing agent would be our zinc 2 plus 2 electrons, producing zinc solid, and our net redox reaction, we just add them together, the electrons cancel out, and this is, I'm going to write it in red. Right, so this is of course a non-spontaneous reaction for the reasons that I outlined when we were there, looking at the data booklet. So if we did look at the reverse reaction, so zinc solid plus lead 2 plus, now that would be a spontaneous reaction, but it does not occur because neither our zinc solid or lead 2 plus ion is there. So that's why you really had to be careful about how you write down the entities, because if you write down an entity wrong and you put it into an equation, it could mess everything up. Right? So just be very careful about writing out your entities. And then of course, don't forget to consider presence of water, because normally in these electrolytic cells, water is often a reactant. So that's just something to be careful for. Now, as I was saying in the table here, comparing two of these right here, as you know, in voltaic cells are spontaneous, electrolytic are non-spontaneous. The standard cell potential is going to be positive for voltaic and negative for electrolytic. Now, the only ones I left blank here are the only ones that are different. Because the direction of the electron flow still go from anode to cathode for both cells, and direction of the anion flow will still be the same as well. Anions go towards the anode, cations go towards the cathode for both. The only difference is the polarity of our electrode. And for voltaic cells, our cathode are positive and our anodes are negative. But for our electrolytic cells, our cathodes are negative and our anodes are positive. And it goes out saying as well, oxidation is still at the anode, reduction is at the cathode. That is definition of what the anode and the cathode are in electrochemical cells. Now, a generic electrolytic cell is going to be set up like this. Now, you will notice that there is no phase boundary. All right, just because we don't need one. It's a non-spontaneous reaction. Now, for our power supply, they always have a positive and negative terminal. Now, remember, our power supply, this is technically a voltaic cell. I don't know why I combined the C at the end, voltaic cell. So, how this works, it's still going to be the same, is that the electrons are still going to flow from the negative terminal because this is where they're originating. The electrons are going to push their way into here and then go down here to our negative terminal, which is the cathode. And what is going to happen is that it's going to draw the electrons from our anode, which is right here. So that is how they're still going to work. Now here we actually have stuff listed like cathode right there, anode here, copper 2 sulfate solution there. So that's generally how they're set up, and like I said, the power source is the main thing right here. Now one thing as well, just be careful for is an ionic solution or a molten ionic solution, because an ionic solution, an aqueous, water is present in molten, no water. All right. So that just means molten is that we heat up an ionic compound so much that it turns into a liquid. So it's a liquid, there's ions floating around, but there's no water is present. So just be careful with those words as well, which we'll see a bunch of examples like that. Now we're just going to go through this example and some of the other ones, and we're going to go over the chloride anomaly, and that'll be it. So when we're asked to draw a diagram and of course fully label and everything like that, is just like the voltaic cells, and of course trying to figure out the half reactions as well, and of course the cell. All right, so let's just read this one carefully. So an electric current is passed through a solution of nickel 2 nitrate using inert electrodes. Predict the anode and cathode reactions, overall reactions, minimum voltage required, and draw a diagram. All right, so that's a lot there, but really when you get going, it's not too bad. So the diagram, we can just kind of keep it simple, 2 electrodes. I'm just going to go power source with PS. They're going to be in solution. They need to be inert electrodes, so I can use carbon. And inside right here, nickel, nitrate, and these, of course, are aqueous. Now, it doesn't really matter how we actually label our anode and cathode, as long as, because really there's nothing here to kind of help say that, just for convention. Let's just have the electrons going this way. So this side is my anode, and this side is my cathode. All right, so anode we know in our electrolytic cells, because of the power source, is going to be positive, cathode is negative. Now to figure out all the entities and stuff like that, we have carbon I'm not going to include because it's an inert electrode. So really, all we have is nickel 2 plus, nitrate, and liquid water. These are all the entities that we have. So now we have to go through the whole song and dance of figuring out, well, what is going to be our strongest oxidizing agent, strongest reducing agent. When you turn to your data booklet and go through, you'll notice that nickel 2 plus is my strongest oxidizing agent. Nitrate does nothing because there's no hydrogen ion, and that leaves water as our strongest reducing agent. So our strongest oxidizing agent is, remember, is reduction. Reduction happens at our cathode. So we have nickel 2 plus 2 electrons producing nickel solid. Now our strongest reducing agent, in this case right here, this reaction at our anode, is water. So water, for that one anyway, you do have to be careful because this one is up here, right? We have this reaction. This is our strongest reducing agent. So we'll write that in. We got H2O liquid producing O2, forgot that. Producing O2 gas plus 4H plus 4 electrons. Now last but not least, to get our cell, we're going to have to do that so the number of electrons cancel out. And our cell reaction, we got 2 H2O liquid plus 2 Ni2 plus, producing O2 gas plus 4 H plus nickel solid. That is that. Then of course, finally, last but not least, we have our, running out of a little space here, we have our cell, and that equation won't change. It's a cathode minus the anode. So I'm just going to abbreviate them cat and ano just because. Now our cathode, and this is why I always label strongest oxidizing agent cathode, and I know it's my nickel. Right, so I go to my data booklet, I find where nickel is. Sorry, I have markings everywhere. I already highlighted the water up here, so I'm just going to do that again. And of course the nickel was somewhere. You guys are probably shouting at the screen right now. It's like, oh, there's nickel, you know where it is. Here it is, nickel's all the way down here. All right, so we got a negative 0.26 volts minus a positive 1.23 volts. So our cathode is our nickel, negative 0.26 volts minus a positive 1.23 volts, and we're left with a massive negative 1.49 volts. And this is the minimum voltage required to start the reaction. So that is how you draw, fully label, and figure out stuff for the electrolytic cells. All right. Now for the next one, an electric current is passed through a solution of potassium iodide. Predict the anode-cathode reaction, overall reaction, minimum voltage required. So this one right here, if you want to actually see how this one looks, please just go to the PDF up on Google Classroom to see what this one will look like, because I think I have that drawn out and everything like that. So that's if you want to see all that, but I just kind of want to jump ahead because drawing these here isn't really much different than the other ones. I want to go on to the last thing for electrochemical cells is something called the chloride anomaly. So what this means is that during electrolysis of a solution containing the chloride ion, when specifically water and chlorine are competing as reducing agents, water technically is the stronger reducing agent, but it is noted if you do this reaction, chlorine gas is produced instead. So just looking at our data booklet, like I said, water is right here. Chlorine is up here. Now, water is a stronger reducing agent, but the chloride anomaly, and this is why it's called anomaly, no one is sure why this happens. Now, there are some theories about, I think, over voltage and stuff like this, but we're not going to get into it. But either way, it is observed that if you do a reaction where both water and chlorine are competing, we end up getting this being produced. So it's the chlorine reaction that actually takes place. So when we look at this, an electric current is passed through a solution of sodium chloride. Predict the anode, cathode half reactions overall and minimum voltage. So sodium chloride, we got Na plus, Cl minus, and because there's a solution, we got H2O liquid. All right. Now going through our data booklets, we will notice that sodium won't do anything. It's too weak. My strongest oxidizing agent is water. Now, normally you would be very tempted to, once again, pick water again as strongest reducing agent, but because of the chloride anomaly, we have to pick chlorine. So that is my strongest reducing agent because of the chloride anomaly. So the strongest oxidizing agent reaction is water. So that's that half reaction. Strongest reducing agent in this case right here is the chloride ion because of the chloride anomaly. And of course our cell reaction, we can just add two of these together because the electrons match out. We got 2 H2O plus 2 Cl minus, producing H2 gas plus Cl2 gas. And of course the cell, we go cathode minus our anode just like before, and of course we put in the values for our cathode and our anode. So our cathode, we know reduction happens at the cathode. That is our strongest oxidizing agent. So that is water, and if you look at your data booklet, it's negative 0.83 volts, and minus our chlorine 1.36 volts, and we're left with negative 2.19 volts. And that is the chloride anomaly. And of course, this right here didn't ask to draw one, so we could have just did all that right away. So that is the chloride anomaly. So just be a little careful with that. Keep that in the back of your mind as you're going through stuff. Just if you see Cl minus, that is there. Now, with these here, there are a lot of similarities between the voltaic and the electrolytic. But how we draw them, that's just one thing, so we don't need that porous boundary for our electrolytic. But how we figure out our anode and cathode half reactions and our cell reactions is the same. It's stuff we've been doing since we started looking at half reactions. The 5-step method to predicting reactions, that's what this is right here, writing stuff down, finding our strongest oxidizing agent and reducing agent, and then just going through. So of course there are some old diploma examples that we have right here, 20 and 21. So you should probably pause the video and give them a go, just see if you can get them. And then of course I'll put the answers up in 3 seconds. And our answers will look something like this. So for the voltaic cell, the only thing that's true here, it requires a type of salt bridge, and electrolytic cells requires an external power source. So this right here is false, converts chemical energy into electron. That's true for B, but moves anions towards the cathode. Nope, anions go towards anode, not cathode. So it's just a matter of kind of figuring which one's true and which one's false, and doing that. And finally, last right here, so the half reaction of the hydroxide ions undergoes in this electrolysis. With this right here, actually, when you look at it, it's telling you that hydroxide ion is undergoing electrolysis. And when you look at C and D, hydroxide's being produced, it's not undergoing electrolysis, so it can't be these here. And for B, we need hydrogen gas, which when you look at this here, it's not saying anything about hydrogen gas is used in this thing. So how can this exist? So basically by process of elimination, we get A. But then also if you did use your data booklet and you found this and you did that with the sodium hydroxide and everything like that, you would find out that this would be the reaction for it, because it is being the AgS solid is going to be reduced, and therefore the hydroxide is oxidized. So that is it for this week. Next week we are going to be looking at cell stoichiometry and just finishing off our electrochemistry unit. I know there's a lot this week. The electrochemical cells is a lot of work. So please make sure you are doing your workbook as much as possible. And if you have any questions, make sure to email me right away. And please, Thursday, try to come in for our extra help session at 12:30, just so you can ask any questions if need be or if you have any trouble. All right, so I'll see you guys next week for cell stoichiometry.